Welcome back to mathkernel. This is the last big Euclidean topic, the spectral theorem. We start concrete. Orthogonally diagonalize symmetric matrices, classify definiteness by eigenvalues, read off the principal axes of a quadric. But the second half is where the real depth lies, and where most notes go quiet. Self-adjoint maps on an abstract space. The AᵀF F equals FA criterion, and the flagship proof that a form is a scalar product exactly when a map is self-adjoint with positive eigenvalues. 12 problems. Pause whenever you want to try one. Problem 1. The fact that makes the whole spectral theorem tick. For a symmetric matrix, eigenvectors belonging to different eigenvalues are automatically perpendicular. Prove it, then see it on a 2x2. Pause and try. The proof is a single quantity computed two ways. Take the scalar product of AV with W. Since V is an eigenvector, AV is lambda V, so this is lambda times V with W. Now slide the A across to the other side. In general, that turns A into Aᵀ, but A is symmetric, so Aᵀ is just A, and AW is mu W. So the same quantity is also mu times V with W. This is the step worth saying out loud. I am using that A equals its transpose. Set the two expressions equal. Lambda minus mu times V with W is 0. The eigenvalues are different, so lambda minus mu is non-zero. The only way the product vanishes is V with W equals 0. The eigenvectors are orthogonal. Concretely, for the matrix 3, 1, 1, 3, the eigenvalues are 2 and 4, with eigenvectors 1, minus 1, and 1, 1. Their scalar product is 1 minus 1, 0, perpendicular, exactly as promised. Problem 2, the core recipe. Turn a symmetric matrix into A equals QDQᵀ, with Q a rotation and D the eigenvalues. Pause and run the recipe. Step 1. The characteristic polynomial. The determinant of a minus lambda I is 4 minus lambda squared minus 1, which expands to lambda squared minus 8 lambda plus 15. Factor lambda minus 3 times lambda minus 5. The eigenvalues are 3 and 5. For each, solve a minus lambda I times the vector equals 0. Lambda 3 gives 1, minus 1, lambda 5 gives 1, 1. And notice, they're already perpendicular, guaranteed by problem 1, since the eigenvalues differ. Normalize each to unit length and stack them as the columns of Q. Because they're orthonormal, Q is an orthogonal matrix. Its transpose is its inverse. D is the diagonal of eigenvalues, in the matching order. And that's the orthogonal diagonalization. A equals QDQᵀ. Geometrically, Q rotates the eigenvectors onto the axes, D stretches along them, and QT rotates back. Every symmetric matrix is a rotation, a stretch, and the reverse rotation. Problem 3, the subtle case, a repeated eigenvalue. The spectral theorem still gives an orthonormal eigenbasis, but you have to build orthogonality inside the repeated eigenspace yourself. Pause and try. Notice A is the identity plus the all ones matrix J. The all ones matrix has eigenvalues 3, 0, 0, so A has eigenvalues 4, 1, 1, a simple 4, and a doubled 1. The simple eigenvalue 4 is easy. Its eigenspace is the line through 1, 1, 1, normalized to U1. The repeated eigenvalue 1 has a two-dimensional eigenspace, the whole plane x plus y plus z equals 0. Any basis of that plane consists of eigenvectors, for instance 1, minus 1, 0, and 1, 1, minus 2. Here's the key move. Within that eigenspace, the vectors need not come out orthogonal, so you Gram-Schmidt them. These two happen to already be perpendicular. Check. 1 minus 1 plus 0 is 0. So you only normalize, giving u2 and u3 with denominators root 2 and root 6. Stack all three as columns of Q. Put 4, 1, 1 on the diagonal of D, and A equals QDQ transpose again. The one thing the repeated case demands: orthonormalize inside the eigenspace. Everything else is the same recipe. Problem 4. The eigenvalues tell you everything about definiteness, and definiteness is what decides whether a symmetric form is a scalar product. Classify three matrices. Pause and try. The rule is pure sign reading of the spectrum. All eigenvalues positive, positive definite. All negative, negative definite. A mix of signs, indefinite. And the count of plus and minus signs is the signature. Matrix A, 3, 1, 1, 3. Eigenvalues 2 and 4, both positive, so positive definite. Signature 2, 0. This one does define a scalar product. Matrix B, 1, 3, 3, 1. Eigenvalues 4 and minus 2, opposite signs, so indefinite. Signature 1, 1. And because it's indefinite, there's a witness. Along 1, minus 1, the quadratic form is 1 minus 6 plus 1, minus 4, negative. That single vector proves it can't be positive definite, so it is not a scalar product. Matrix C, minus 2, 1, 1, minus 2. Eigenvalues minus 1 and minus 3, both negative, negative definite. Signature 0, 2. Read the signs, and definiteness is immediate. Problem 5. The spectral theorem as geometry. A tilted conic is just a diagonal one, rotated. Diagonalize its matrix to straighten it out and read off the axis. Pause and try. First, read the quadratic form as a symmetric matrix. The x squared and y squared coefficients go on the diagonal. The cross-term coefficient, split in half, goes off diagonal. So m is 5, 2, 2, 5. Diagonalize it. The eigenvalues are 3, along the direction 1, minus 1, and 7, along 1, 1. Those two perpendicular eigendirections are the principal axes of the ellipse. In coordinates aligned with those axes, the equation straightens to 3x tilde squared plus 7y tilde squared equals 9, a standard and tilted ellipse. Now the semi-axis. Each is the square root of 9 over the eigenvalue. Along the 3 direction, root 3. Along the 7 direction, 3 over root 7, which is shorter. The bigger eigenvalue squeezes the ellipse harder. The eigenvectors are the axes. The eigenvalues set the widths. Problem 6. A matrix with distinct eigenvalues is diagonalizable, but is it orthogonally diagonalizable? Test a non-symmetric one and see exactly what breaks. Pause and try. Find the eigenvalues. The matrix is triangular in effect, so they're just 2 and minus 1, distinct, so C is diagonalizable. The eigenvectors are 1, 0, and 1, minus 1. But now check orthogonality. Their scalar product is 1, not 0. The eigenvectors are not perpendicular. They sit at 45 degrees. So C is diagonalizable, but not orthogonally diagonalizable. There's no orthogonal Q that diagonalizes it. And the reason is exactly problem 1 in reverse. The orthogonality of eigenvectors came from symmetry, and C is not symmetric. Distinct eigenvalues buy you diagonalizability. Only symmetry buys you an orthonormal eigenbasis. Problem 7. Now we leave matrices behind. A map is self-adjoint if it can move across the scalar product without changing anything. Prove it straight from that definition. Pause and try. The definition, phi is self-adjoint if, for all x and y, the scalar product of phi x with y equals the scalar product of x with phi y. The map slides across the bracket untouched. Let's just compute both sides for this phi. Left side. Phi x is the number x with a times the vector a. Pull that number out of the bracket. X with a times a with y. Right side. Phi y is y with a times a, so x with phi y is y with a times x with a. Both sides are the product of the same two numbers, x with a and a with y, just written in the other order, which for real numbers is identical. So the two sides agree for every x and y, and phi is self-adjoint. No basis, no matrix, straight from the definition. This map, by the way, is projection onto the line through A, and orthogonal projections are always self-adjoint. Problem 8, and this is one your professor loves. When the scalar product is a general matrix F, self-adjointness is no longer just a symmetric matrix. Derive the real criterion and test it. Pause and try. Start from the definition, but with the F scalar product, phi x with y, in the F product equals x with phi y. Write everything in matrices. The F product of two vectors is the first transposed, times F, times the second. So the left side is EX transposed, F, y. That's X transpose, A transpose F, y. The right side is X transpose, FA, y. These agree for every x and y exactly when the middle matrices are equal. A transpose F equals FA. That is the self-adjointness criterion for a general scalar product, not A equals A transpose, but A transpose F equals FA. When F is the identity, it collapses back to plane symmetry. Test our A, 2, 2, 1, 0. A transpose F is 5, 4, 4, 2. And FA is also 5, 4, 4, 2. They match, so this non-symmetric matrix A is self-adjoint with respect to the F scalar product. This exact move, justify A transpose F equals FA, has shown up in the two most recent exams. Learn it cold. Problem 9. The adjoint is the map that lets phi cross the scalar product. For the standard product, it's just the transpose, but for a general product, it's not. Derive both. Pause and try. The adjoint phi star is defined by one condition. Phi x with y equals x with phi star y for all x and y. Find the matrix of phi star in each case. Case 1, the standard product. X transpose times y is x transpose times A transposed y. So the adjoint's matrix is simply A transpose. That's the familiar fact. Over the standard product, adjoint means transpose. Case 2, the F product. Let phi star have unknown matrix B. The left side is X transpose A transpose Fy. The right side is X transpose Fby, matching the middle matrices. A transpose F equals Fb. Solve for B. Multiply by F inverse on the left. The adjoint's matrix is F inverse, A transpose, F. The transpose gets conjugated by F. That's the general adjoint. And this closes the loop with problem 8. Self-adjoint means phi star equals phi, that is B equals A, which rearranges to exactly A transpose F equals FA. Same criterion seen from the adjoint. Problem 10, the hardest one in the set, and the one that really tests whether the idea has landed. On an abstract space, not on Rn, prove the equivalence. Pause and try to structure both directions. Two things make beta a scalar product: symmetry and positive definiteness. Bilinearity is automatic. Take them in turn. Symmetry, beta of V, W equals beta of W. V means phi V with W equals phi W with V. But by symmetry of the underlying product, phi W with V is V with phi W. So symmetry of beta is exactly phi V with W equals V with phi W for all V and W. And that is the definition of self-adjoint. So beta is symmetric if and only if phi is self-adjoint. First half done. Now positive definiteness. And here the spectral theorem does the heavy lifting. Because phi is self-adjoint, there's an orthonormal basis of eigenvectors, bi, with real eigenvalues lambda I. Evaluate beta on a general vector, v equals sum of xi bi. Phi hits each bi and pulls out its lambda I. And because the bi are orthonormal, all the cross terms vanish. What survives is beautifully clean, the sum of lambda I times xi squared. This is the crucial line, and it must be done on the abstract space, not by secretly replacing v with Rn. Read it off. That weighted sum of squares is positive for every non-zero vector exactly when every eigenvalue lambda I is positive. And the other direction comes with a witness. If some eigenvalue lambda I naught is 0 or negative, then beta of that eigenvector with itself is exactly lambda I naught, which is not positive, so beta fails to be a scalar product. Both directions proven. The picture is the bowl. Beta with itself is a sum of lambda-weighted squares, and it opens upward precisely when all the weights are positive. Problem 11, the one-point follow-up that trips people. Find a single basis that is orthogonal for both scalar products at once. The work is already done, you just have to see it. Pause and try. Don't build anything new. Reach for the eigenvector basis you already have from the previous problem. It's orthonormal for the original product, and its vectors are eigenvectors of phi. By construction, it's orthogonal for the original scalar product. Bi with bj is 0 whenever I and j differ. Now check beta on two different basis vectors. Beta of bi and bj is phi bi with bj, which is lambda I times bi with bj. And bi with bj is already 0 for different indices, so beta of bi and bj is 0 too. So the very same basis is orthogonal for both beta and the original product. The key is that the correction note warns against. This does not just follow from the spectral theorem, because that theorem knows only one product. You have to exhibit the eigenbasis and check beta on it directly. One basis, two geometries. Problem 12. The finale, two ways to certify a symmetric matrix is positive definite. Factor it as R transpose R, or take its spectral square root. Pause and try. First, Cholesky. Write F as R transpose R with our upper triangular, entries R, S, on top, 0, T below. Multiply it out. The top left is R squared, the off diagonal is RS. The bottom right is S squared plus T squared. Match to F, which is 4, 2, 2, 5. R squared is 4, so R is 2. RS is 2, so S is 1. S squared plus T squared is 5, so 1 plus T squared is 5, T is 2. So R is 2, 1, 0, 2, and F is R transpose R. The mere existence of this real triangular factor certifies F is positive definite. That's the Cholesky test. The second certificate is the spectral square root. Take the matrix A from problem 2, already diagonalized as QDQ transpose with eigenvalues 3 and 5. To take its square root, just replace each eigenvalue by its square root. Root A is Q, diagram of root 3 and root 5, Q transpose. Squaring it brings back D, hence A. Because the eigenvalues are positive, their roots are real, so a positive definite matrix always has a genuine square root. Two certificates, same conclusion. Positivity you can hold in your hand. That's the spectral theorem, concrete and abstract. The concrete half. Symmetric matrices orthogonally diagonalize. Eigenvalues classify definiteness, and eigenvectors are the principal axis. The abstract half. The half that matters most. A map is self-adjoint when it slides across the scalar product, which in matrices is A transpose F equals FA, not mere symmetry. The adjoint is F inverse A transpose F, and a form built from a self-adjoint map is a scalar product exactly when its eigenvalues are positive, proven on the abstract space with the sum of lambda x squared. Master that arc and you own the hardest task on the paper. If it helped, give it a like and tell me in the comments which to slow down. Support the channel on Patreon, link below. Thanks for watching, one more set to go.